As you might have noticed, I have skipped quite a few slides. These slides are about the simplex method and duality, so how the solutions of the primal problem and the dual problem are linked through this simplex method. These slides are there for your information only. We have seen previously that to start the simplex method we need an initial basic feasible solution, and in some cases, as we have seen, it is immediately available. This is always the case, for instance, if you have a problem where all the constraints, right, are of the type smaller or equal than, because this means that in every of the inequations you'll have to add a slack variable, and this slack variable will only appear once in the underlying equation and it will not appear in the other equation. So you can use the slack variables as basic variables, and a basic feasible solution is then very easy. This has been the case in all our exercises so far. Well, often an initial basic feasible solution is not always apparent, and what we'll have to do is to solve an auxiliary or artificial linear program to find this required initial solution. Let us have a look at an example that comes from the exercises available on the web page of the course. So above you have the original problem. Note that this original problem has 3 constraints and the types of the constraints are different. You have larger or equal, smaller or equal, and equal. So in blue what you see is the problem in its standard form. The original problem is a minimization problem, so this means that the standard form will also be a minimization problem. In the first inequality, we have larger or equal, so we should use here a surplus variable x4. In the second inequality we have smaller or equal, so this is a surplus variable and this is a slack variable that is added, and the last constraint is already an equality constraint. Of course we can leave it as is, but if you look at this standard problem, it is not possible to find very easily an initial feasible basic solution, right? So what you can do here is use x5 as a basic variable because it only appears once in an equation with the coefficient 1. You could say x4 is only appearing once as well, but it's appearing with the sign or the coefficient -1, right? You could say I'm going to multiply by -1, but then you'll have on the right hand side a -1, and we know that the b coefficients have to be positive, right? So difficult to find here an initial basic feasible solution, and only x5 can be used as a basic variable. So what we'll do is introduce an auxiliary problem. Well, we have seen that x5, that is over here, can already serve as a basic variable. So we have already one basic variable, but since we have 3 constraints, we need 3 basic variables. So we'll need to add 2 so-called artificial variables, x6 that we'll add in the first equation and x7 that we'll add in the second equation. And for these 3 constraints now we have a basic feasible solution. It is x5 is equal to 5, x6 is equal to 1, and x7 is equal to 1. All the other variables, x1, x2, x3, and x4 can be set to 0. So this is a basic feasible solution to this problem over here. And of course, we want to find a solution for which x6 plus x7 is 0, so as small as possible. So what we'll do is minimize the artificial cost x6 plus x7. If this has a solution where x6 and x7 are 0, well, this will produce an initial basic feasible solution for our problem over here. In general, you'll have to proceed as follows. You start from the original problem, you bring it into its standard form, and then you obtain a set of equations. Ax is equal to b, x non-zero, and b positive, right? This is important that you check that this is the case. If one of the b's is negative, multiply the underlying equation by -1. Then you have to find an initial basic feasible solution. So you have to look for a basic variable in each equation, and sometimes you will not find such a variable for each equation. In the equations for which you do not have a basic variable, you'll have to add an artificial variable. So in general, you'll add m bar artificial variables, and m bar is smaller or equal to m. M is the number of constraints. At most, you will add an artificial variable in each equation, right? In the artificial minimization problem, you'll choose the criterion, the objective function, to be the sum of the artificial variables. And since you're adding artificial variables, well, the constraints are adapted. The artificial variables are stacked in y, and y is also constrained to be non-negative. Well, if we consider the example that we have treated before, we have added two artificial variables, so m bar is equal to 2. We can stack the variables in y. We had two artificial variables, x6 and x7, and the way we had adapted the constraints is as follows. We had use ay is equal to 1 0 0 0 0 1, and this is because x6 is introduced in the first equation, whereas x7 is introduced in the last equation. Ay times y is 1 0 0 0 0 1 times x6 x7, and that's equal to x6 0 and x7. As you can see, we have indeed added the variable in x6 in the first equation and x7 in the last equation, and we have left the second equation untouched because we had already a variable that can act as a basic variable, and this was x5. So if in the original minimization problem we have a feasible basic solution, then the artificial problem will lead to an optimum cost that is 0, and all the artificial variables will be 0. If the original problem does not have a feasible basic solution, then the cost will be larger than 0, and some of the artificial variables in the optimal solution will be larger than 0. Note that the artificial minimization problem that we have presented here is itself a linear program, and by construction it is in canonical form, and this means that it's easy to find a starting basic feasible solution. Obviously you will use the simplex method to solve this artificial minimization problem, and at each stage, at each step, you'll find a new basic feasible solution, and this will also be the case, of course, at the optimum. If the optimum corresponds to a 0 cost, right, this means that all the artificial variables will be 0, right? So you'll find a final basic solution that is, well, feasible, of course, and in which all the artificial variables are set to 0. So let us consider this problem. It's a minimization problem. We have equality constraints, so the problem is in its standard form already, but as you can see, it's difficult to find an initial basic feasible solution as the variables appear in the two equations, right? So it's kind of difficult to see which variables you should choose as basic variables and how you would then obtain the basic solution. So what we'll do is add artificial variables in the first and second equation, respectively x4 and x5, which are constrained to be non-negative, and we'll deal with this artificial problem here that minimizes the sum of the artificial variables. Notice that in this case it's easy to find an initial basic feasible solution, right? So in our case here we have m bar is equal to 2, that's the number of artificial variables, and it's also equal to m, the number of constraints. We can stack the variables in y, x4 and x5, and to be able to write this as follows: the matrix AY is simply here the identity matrix. So AY is obviously x4, x5. This is simply saying that we are adding a variable x4 in the first equation and a variable x5 in the second equation, right? If this original problem has an initial basic feasible solution, this artificial problem will have an optimum in which, well, x4 and x5 will be 0, so the objective function will be 0. And as I said before, by construction it's easy to find an initial basic feasible solution. The basic variables will be x4 and x5, the artificial variables, and the non-basic variables will be x1, x2 and x3, which you can then set to 0. This is the basic solution you can start from, and you can then read, well, the value of x4 from the tableau. So x4 is equal to 4 and x5 is equal to 3. So this is the artificial problem that we've ended up with, and we consider this to be the problem of stage 1. And of course, to solve this we have to write this as an initial simplex tableau, and over here you have the two constraints, right? And what we do is write the cost, right? We had said that x4 and x5 are the basic variables, so these are the pivots, and this time we have to pay attention. We cannot start to see here which variable has to join the base by looking at this thing here, because we do not have zeros below the pivots. So what you should do is, well, make sure that in this third line we have zeros below the pivots, and we can do this by elimination, right? So what we'll do is this operation, this is the element to eliminate divided by the pivot, so the multiplier is 1, and then you do something similar, right? So do not forget to do this at the time of the exam, and this is needed to initiate the simplex procedure, because we want to have the simplex tableau in its canonical form. Canonical form means that there are zeros above and below the pivots. Once you have brought this initial simplex tableau in the canonical form by doing these elementary operations, you obtain the second tableau, and now you proceed as usual. What you have over here is R1, R2 and R3, right? These are the reduced costs, and you can see that they are negative, so we are not at the optimum yet. And what we do is select the R that is the most negative, so this is obviously this one over here, and then we compute this ratio. This is this element divided by this one, that's a 2, and this element divided by this one, that's a 1. So the smallest non-negative element in this column is 1. So this selects now this row, and as you can see, our pivot here is 3, right? So we can see that x1 is going to join the base, and as you can see over here, well, the variable x5 is going to leave the base, right? So what we should do is to do elementary operations to create zeros above and below the pivot. Here are these elementary operations. It's the same as usual. You have a minus here. The element to eliminate, divide by the pivot. This is the multiplier. And here we have to eliminate the minus 5, and the pivot is 3, so minus 5/3, right? So what you do is this first equation, or first row, minus 2/3 times the second row. And of course you want a pivot of 1 over here, so you'll have to multiply this second row by a third. Well, if you do the calculations and you perform these elementary operations on the tableau, you obtain the third tableau, and as you can see here, R3 is still negative, so this means that we are not yet at the optimum, right? So we can see here that x3 can enter in the base, so we need to determine which variable has to leave. For that we do the usual trick. We compute this column, and it's this element divided, yes, by 4/3, right? So this is 6/4. This element divided by this one, so that's a 3, right? So this is equal to 2. So the smallest one is this one over here. So this selects this row, and we had selected this column. So this is why, well, 4/3 will be the pivot, and you can kind of see that x4 is going to leave the base, which is good because this is what we expect. We expect an optimal solution in which, Well, x4 and x5 are non-basic variables that you can set to 0, right? So again, we can do the elementary operations that are given over here, and they are meant to create zeros below the pivot. And if you do these elementary operations on the third tableau, you'll obtain the fourth and final tableau, which is given over here, and you can see that it's the final tableau because all the elements in the last row are positive, right? And what is nice is that you can see here that the cost is indeed 0, right? And that, well, the artificial variables have become non-basic, so they can be set to 0. So the optimal solution here is x2 is equal to x4 is equal to x5 and is equal to 0, of course. And then you see basic variables in x1 and x3. So we have x1 is equal to, you can see it over here, a half, and x3 is equal to 3/2, right? So this is the solution of this artificial problem. So this means that we have now an initial basic feasible solution to our original problem, which is x1 is equal to a half, x2 is equal to 0, and x3 is equal to 3/2. So what we'll be able to do now when we continue is to cross out this column, because it is associated to artificial variables, this row over here, okay, because it is associated to the cost in our artificial problem, and we'll keep the rest, and below these two lines here we'll write the original cost. And indeed, in this final tableau, the artificial variables x4 and x5 have been driven out of the base. The objective function is 0, and this leads to a basic feasible solution to the original problem. And of course, you should check this. Well, let us do this check. x1 is equal to a half, x2 is equal to 0, and x3 is equal to 3/2. And if you plug this in, well, you have 1 over here and 3, that's 4, that's correct. Here you have 3/2 and 3/2, that's 3. So indeed, this is an initial basic feasible solution to our initial problem. So when it's not easy to find a basic feasible solution, we use the two-phase method, right? And in phase 1, we construct the artificial problem and we solve it, and this will lead to a basic feasible solution for the original problem. And then we start phase 2, in which we remove, of course, the artificial variables, we remove the artificial cost, and we use the cost of the original problem. And this leads to a second linear program that will lead to the solution of the original problem. Well, let us return to this linear program that we're trying to solve. Remember that in the first stage, as there was no basic feasible solution apparent, we have introduced an artificial optimization problem, an artificial linear program that takes this form. This is the stage 1 problem, this artificial problem that introduces two artificial variables x4 and x5, but it can be treated as a simple linear program, and you can use the simplex method to solve this problem. At the end, you will obtain an initial basic feasible solution for your original problem. Well, this is the final tableau of stage 1, and as you can see, we have found an initial basic feasible solution of the original problem, and here it is, right? So what we'll do now is skip the last columns because they are associated to the artificial variables of the stage 1 problem, and both variables are 1 now. We'll also remove the last line because it's related to this artificial cost, and we'll introduce the cost of the original problem. So here 4, 1, 1 and a 0 over here. And this is how we obtain the initial tableau of phase 2, right? But pay attention, this tableau is not yet in its canonical form because you can see that we have the basic variables x1 and x3 and associated pivots, but you do not have zeros below the pivots. Okay, so you have to do 2 elementary operations to create zeros here in this last line below the pivots, right? And here you have these elementary operations, and this is how you obtain the second tableau. And from here on, well, everything starts as in the simplex algorithm, right? So we have here R2 that is negative, which is saying that, well, the initial basic feasible solution is not optimal. We can make sure that x2 is entering the base, and of course we have to look at which variable is going to leave the base. And as usual, we compute this column, so it's this element divided by this one, that's -2, and this one over here divided by this one, and that's 2/5. And then in this column you select the smallest but positive element, and it's clearly this one. We have now selected the variable x2 that is going to join the base, and from this row we can see that the variable and the old pivot, this is the old pivot, well, the variable x1 is going to leave the base, and this means that this element 5/4 is the new pivot, and of course we have to create zeros above and below this pivot. This corresponds to these 2 elementary operations, and I assume by now that you can do this. And you have to multiply the second line by the inverse of the pivot. Well, if you do these elementary row operations, elimination operations, you find the third and final tableau. It's the final tableau because you can see here that the R coefficients are all positive, hence the solution is optimal, right? And how do you find this optimal solution? Well, this is a non-basic variable, so you set x1 to 0, and you can read the solution from the tableau. x3 is 9/5, this is what you have over here, and x2 is 2/5, and this is what you read over here. Of course, what we should do now is look and see if this optimal solution meets the original problem, to see if we have not made any mistakes. Of course, we can also read the optimal cost. You take this value here, but this is minus the optimal cost, so the optimal cost associated to our minimization problem is 11/5. So let us write again the solution and check. x1 is equal to 0, x2 is 2/5, and x3 is 9/5, and the optimal costs, is, well, 11 over 5. So let us check first the first constraint, right? We have 2 over 5 plus 18 over 5, 20 over 5, that's 4, so that's okay. Let us check the second equation here. We have 6 over 5 plus 9 over 5, that's 15 over 5, that's a 3, that's correct as well. And if we plug the values in the costs, well, you can see that you will have 11 over 5, so this seems to be okay as well. So again, we can check with Matlab. This is the cost function. We have now equality constraints, right? So they appear over here, and here we have the, well, non-negativity constraints on the 3 variables. Again, we use the Simplex algorithm, and this is what you obtain. So again, you have x1 is equal to 0, x2 is 2 over 5, x3 is 9 over 5, and the cost is, well, 11 over 5, so this seems to be correct. I've shown you in other courses that it's possible to work with Python, and this is also the case in this course of optimization. Well, the easiest is to install the Anaconda navigator. You'll find quite a lot of information on how to do this on internet. Once it is installed, you can use the JupyterLab environment to start programming in Python. So we'll launch this environment. And over here you can see the code that I've prepared to solve the linear program that we have just treated. Well, to run this code, you have to import the pulp environment, and the pulp environment you will have to install it, and you can do this by running the following code from the Anaconda shell prompt. And pulp is a library that you can use for optimization, and then things are rather straightforward. You define the variables, the cost function, the constraints. You can use equality, inequality constraints, smaller or equal, larger or equal, and then you just solve the problem. When you have a 1, then everything is terminated correctly, and then you can have a look at the costs and the value of the solution, and obviously we find the same solution as in the slides and as with Matlab. Let us do an exercise. This is an exercise of the type that you will have at the time of the exam. Try to do this exercise by yourself, so push the pause button and take a piece of paper to solve this problem. Well, the first thing that you have to do is to bring this original problem in the standard form, and the problem that we have here is that we have a -1 over here, and remember that in the standard form the coefficients in the b vector have to be positive. So what we'll do is multiply this constraint by -1 and replace it by this equality constraint that is now a constraint larger or equal than. Well, we have 2 constraints that are now larger or equal, so this means that in the first equation we have to use a surplus variable, and this is also the case in the second equation. And in the third equation we have smaller or equal, so there we can add a slack variable. Okay, so if we want to find an initial feasible basic solution, this is difficult over here. And as you can see, well, the only variable that appears once in the equation and that has a positive coefficient is x5. So x5 will be able to act as a basic variable. but in the two other equations, well, we have no candidates, so we'll have to, well, write an artificial problem, and in this artificial problem we'll have to add an artificial variable in the first equation and in the second equation. So indeed we obtain an artificial problem in which we have added two artificial variables, x6 and x7, x6 in the first equation, x7 in the second equation, and you can now very easily find, well, three basic variables, and they are x6, x7, x5, right? And the cost that we have to minimize is, well, the sum of the artificial variables. And if this problem in standard form as an initial basic feasible solution, well, the solution of this artificial problem and the optimal solution will be one that involves x6 is equal to 0 and x7 is equal to 0, so the optimal cost will be 0. What we can do now is write this artificial problem, and this is then the start of phase 1, in a tableau, as you can see over here. And here you have the cost x6 plus x7. You can see here that you have the basic variables x5, x6 and x7, right? But this tableau is not yet in its canonical form because we have to produce zeros over here, so you should not forget this. So what we will have to do is do elementary operations of this type, right, with a multiplier that will be 1, and then there is another elementary row operation, and it's this one over here, with also a multiplier that is 1, and this will lead to the second tableau. Well, if we do the elementary operations that you see over here, we end up with the second tableau that is in canonical form, so we can now start the simplex method. You can see that the basic solution is x1 is equal to x2 is equal to x3 is equal to x4 and is equal to 0. These are the non-basic variables, and you can see here that x5 is equal to 2, x6 is equal to 1, and x7 is equal to 1 as well. You can read this from the second tableau, right? And you can see that indeed the cost is, well, the opposite of this value, 2, and indeed if you have x6 is equal to 1 and x7 is equal to 1, then the sum leads to 2. So here we have this second tableau, and what you see over here is R1, and R1 is negative, so it makes sense to make sure that x1 enters the base. To see which variable has to leave the base, we compute yi0 divided by yi1. So it's this one by this one, so that's a 1, this one by this one, that's a half, and this one by this one, this is, well, infinity, right? And the smallest one is therefore this one over here, right? So the new pivot is over here, right? And we can see that, well, it will be x7 that will leave the base. So what we need to do is create zeros above and below the pivot. So we'll have here with a multiplier that is a half, right, and another elementary operation with a multiplier that is the element to eliminate over the pivot, so it will be minus 3 over 2. After calculation, you obtain the third tableau of phase 1, and you can see that R2 is negative, so we still have not obtained the optimal solution. You can see that, well, x2 will enter the base, right? And we have to find out which variable has to leave the base. So we have to compute the column yi0 divided by yi2. This is to compute this epsilon of step 2 of the simplex method, right? So it's this element divided by this one, that's a third. This one divided by this one, that's minus 1. And this one divided by this one, that's 2/3. And of course we are going to select the smallest one, that is non-negative, right? So this means that the pivot will be 3/2, right? And that's, well, the old pivot is 1, so x6 will leave the base, right? So now we have to look at the elementary operations that we have to perform to create zeros here below this pivot, and we'll have, you take the element to eliminate divided by the pivot, so here we'll have minus 1/3. So here the multiplier will be 3/2, so simply 2, and we still have to create a 0 in the last line, so it's the element to eliminate divided by the pivot, and here that's a minus 1. Of course, what you'll have to do is to multiply the first line by the inverse of the pivot, that's 2/3. And if you do the calculations, well, you end up with the final tableau, and as you can see over here, well, the optimal cost is equal to 0. The artificial variables are outside of the base, and therefore in the optimal solution we have that the non-basic variables and the artificial variables are among them are all set to 0, and this leads to, well, an initial basic feasible solution for our initial problem, and this solution can be read from the tableau, right? x2 is a third, x1 is 2/3, and x5 is 1. So let us check if this solution meets our original problem. In fact, you should do this kind of check at every stage. So let us return to our initial standard problem. We have found as initial basic feasible solution x1 is equal to 2/3, x2 is equal to 1/3, x3 is equal to x4 is equal to 0, and x5 is equal to 1, and we should look if this meets the original, well, constraints. And as you can see, this is okay for the first one, 2/3 plus 1/3, it's 1. 4/3 minus a third is 1 as well, and 3 times x2, that's 1, plus x5, 1 is also equal to 2. So this means that we can continue with the second phase of the problem. Well, to continue with phase 2, what we'll have to do is, well, cross out the 2 columns that correspond to the 2 artificial variables. We'll forget about this artificial cost, and here below we'll have to write the original cost, and this original cost is 6x1, so we'll have a 6 here plus 3x2, and all the other elements will be 0. Well, this is this first tableau that we had constructed for phase 2, and as you can see, I've got the basic variables x1, x2 and x5. I've got a pivot over here, one over here and one over here, but the problem is that this tableau is not in canonical form because we should have zeros below the pivots. So what we'll have to do is do row operations to bring this problem in canonical form. So here we'll have 3, right? And then we'll have to do another row operation to make a 0 over here, and here the multiplier will be a 6. Well, if you do these row operations, you obtain the second and final tableau. You can see that it's the final tableau because the R values that you have over here are all positive. So we have arrived at the optimal with an optimal cost that is the opposite of this value. So it turns out that here the initial basic feasible solution that we have found is also the optimal solution. You have to set the non-basic variables x3 and x4 to 0, and again you can read the solution from the final tableau. x2 is 1/3, x1 is 2/3, and x5 is 1. Well, if we go back to the original problem, we have found the optimal solution. x1 is equal to 2/3 and x2 is equal to 1/3. If you plug this in the cost, well, you'll have 4 and 1, and that's 5, so that's correct. And you can see that if you plug this optimal solution in the two inequalities, you will see that they are met with equality, and you could see this from the fact that x3 is equal to 0 and x4 is equal to 0 over here, right? And this means that these two inequalities are met with equality. Whereas if you plug this in the last inequality, well, you have 3 times 1/3, that's 1. So here you have indeed an inequality and you have a slack of 1, and this is what this x5 is equal to 1 means. Well, let us do another exercise, and here it is. Again, this is a two-stage problem that you can solve with the simplex method. Try to do this by yourself and push the pause button. Well, the first thing that we have to do is transform the problem in its standard form. Over here you can see that you have b3 that is negative. We want the b's to be positive, so what we'll do is multiply the equation by -1, and of course instead of having smaller or equal, we have now larger or equal. In the two first equations, since we have smaller or equal inequalities, we have to add slack variables x4 and x5. In the last constraint, since it has now become a constraint larger or equal, well, we have to introduce a surplus variable x6 and x7, and we end up with the following problem in standard form. As usual, we will be able to use the slack variables as basic variables to start from, right? But we have a problem in the third equation because we cannot find a variable that appears once with a positive coefficient in front. So what we'll have to do is add here an artificial variable x7 and minimize the cost x7. So indeed, here's the artificial problem, and as said before, we have added an artificial variable x7 in the last constraint, and we need to minimize a cost that involves the sum of all the artificial variables, but there is only one over here, so we minimize x7. This artificial problem has been written here in the form of a tableau, and you can see very easily that it will be possible for this artificial problem to find an initial basic feasible solution quite easily, because we can use x4 and x5 as basic variables in this artificial problem. This is because they come from, well, slack variables in the original problem. So here in this case we only have to add one artificial variable. Sometimes I see that at the exam people will also put artificial variables in the two first equation and add them in the cost. This can work also, but this will make this artificial problem, well, more complicated than needed. So only add as many artificial variables as needed, and here clearly we only need one, right? So here we can see that the initial basic feasible solution is x1 is equal to x2 is equal to x3 is equal to x6 is equal to 0. These are the non-basic variables, and you can read the basic solution, basic feasible solution from the tableau. x4 is equal to 10, x5 is equal to 15, and x7 is equal to 4. So this is this initial tableau of phase 1. Remember that the idea using this artificial problem is to find a basic feasible solution for this initial problem, and if this initial problem has an initial basic feasible solution, well, the optimal solution of the artificial problem will be a cost of 0, and therefore the underlying artificial variable x7 will be 0. If we look at this initial tableau, we can see the pivots over here, and in the last column here we have a pivot, but we do not have a 0 below the pivot. So this means that this initial tableau is not yet in canonical form. So the first thing that we should do is to make sure that we have zeros above and below the pivots. Do not forget to do this, and for that we'll use an elementary elimination, right, an elementary operation, and here the multiplier will simply be 1. Well, we are now ready to continue with this second tableau after we have, well, brought the system in canonical form, and we have here R1 negative, R2 negative. We'll choose to let the variable x1 that is most to the left join the basis, right? And to see which variable is going to leave the basis, we compute yi0 over yi1. So this one divided by this one, that's 10 thirds. This one divided by this one, that's 15 over 2. And this one divided by this one, that's simply 4. And if you look at the smallest one, it's this one over here. So the pivot is over here, and we can see that, well, x4 is going to leave the base. We have now to create zeros below the pivot, right? So here the multiplier will be 2 over 3, the element to eliminate over the pivot. So another row operation, and here the multiplier will be 1/3, and yet another elementary operation, and here the multiplier will be -1/3, and of course we have to multiply this first line by 1/3, which is the inverse of the pivot. If you do the following elementary operations on the second tableau, you end up with the third tableau. We can see that it's not yet optimal because our 2 here is negative, right? So this means that x2 is going to join the base, and we have to look at which variable is going to leave the base. So we have to compute yi0 over yi2, this one divided by this one, so that's a 5, this one divided by this one, this is a 5 as well, and then this one divided by this one, that's a 2, and the smallest positive value is 2 over here. So we can see that we have a pivot over here, and that x7 will be leaving the base, and this is as expected, right? Because x7 is the artificial variable. So we have a new pivot over here, so what we should do is do the necessary elementary operations to find to have zeros above and below the pivot. So we'll have here with a multiplier 5, here we'll have an elementary operation with a multiplier 2, and we have here an elementary operation with a multiplier -1, right? And what we'll have to do is multiply the whole equation by the inverse of the pivot, so we'll have to multiply by 3. So after having performed the operations, the row operations, we obtained the final tableau, and we can see that the associated cost is 0, and the associated, well, artificial variable is therefore also 0. We can see that the basic variables are x1, x2 and x5. The other variables are non-basic, and you can set them to 0, and you can read the solution in the tableau. x1 is equal to 2, x2 is equal to 2 as well, and x5 is equal to 5. So this is an initial feasible basic solution for our initial problem that we had in the standard form. So what we'll have to do now is cross out the column that corresponds to the artificial variable, and we'll cross out the last row because the cost is associated, of course, to this artificial problem. And what we'll have to do is to add the cost associated to the original problem, and in standard form, after transformation to minimization, we have -2, -3, -4, 0, 0, 0, 0. And indeed, this is the initial tableau of phase 2. Here you recognize the cost from our standard form. Note that this tableau is not yet in its canonical form. You cannot draw any conclusions right now on which variable should join the base, right? Because it is not in canonical form. Indeed, you see here that you have pivots, Over here everything is okay, but as you can see here below the pivots we do not have zeros, so we have to do the following elementary operations, right? So with a multiplier -2 and the following elementary operation with the multiplier -3. After computation of these elementary operations, you can see here that R3 is negative, R4 is negative, and R6 is negative. We'll take the most negative R, so this means that x3 will join the base. We'll compute yi0 over yi3. So that's this one divided by this one, 2/3. This one divided by this one, 5/9. And this one divided by this one is -1/2. And we'll choose the smallest positive ratio in this column. And that's 5/9. So this means that the pivot is 9 over here. And as you can see here, well, x5 will leave the base. So what we'll have to do is do a number of elementary operations to create, well, zeros above and below the pivot. So here the multiplier will be 1/3. In this elementary operation the multiplier will be -4/9, right? And here we'll have yet another elementary operation with a multiplier that is -10/9. And of course we'll have to multiply this second row by the inverse of the pivot, so 1/9. Well, we now obtain the third and final tableau because we can see that all the R elements are positive. So we can have a look at the optimal cost. If we look at the minimization problem, this is the standard problem. We'll have to take this one with a minus sign, but you know that the original problem was a maximization problem, so the associated cost is 140/9. You can see here that the three first variables, which are really operational variables, are the basic variables. So you can read that x1 is 1/3, you can read that x2 is 38/9, and you can read that x3 is 5/9. The other variables that have been introduced in the problem to transform the problem in its standard form are all zeros. So this means that in the original problem we meet the constraints with equality.